Multiple choice question from May, June 20, paper 11, question number 5. Let's see what this question is about. A measurement is taken correctly. Let's look at this. But with a ruler at a significantly higher temperature than that at which the ruler was calibrated. The higher temperature causes the ruler to expand. So there are 3 important information here. One is that the measurement was taken correctly. Another one is that a ruler was expanded, so the marks was expanded because was in higher temperature. What describes the effect on the measurement caused by the higher temperature and how the measurement may be improved. We have 2 questions here. One is the effects on the measurement caused by the higher temperature. That's one question. The second question is how the measurement may be improved. So here is a picture of the ruler when at normal temperature and normal calibration, and here is the same ruler under higher temperature and expanded. So as you see, is a little bit longer than this one. So as a reference, I have a pencil here. So for the regular calibration, and let's say in inches, will be 3 inches, and with the expanded ruler, I will have a smaller reading here, so you'll be less than 3 inches. Okay, so let me look each option, A, B, C, D, the first part of the answer. So there is a repetition here. The measurement will be subject to a random error. B is the same. And C is different, is the measurement will be subject to a systematic error. And D is the same sentence. To answer the first part of this question is random or systematic error. Because this was caused by a instrument calibration, which is this one here, so we say that is systematic error. Another piece of information is the beginning of the story. It says the measurement was taken correctly, so the experimenter did not make a mistake when was doing the measurement. However, the instrument, in this case a expander ruler, was the cause of the error in this measurement. So that's saying this is a systematic error. So going back to the options, we can eliminate A and we can eliminate B because it's not a random error. Now let's take a look on the second answer. The measurement can be made more accurate by taking the average of several repeated measurements. Or the measurement can be made more precise by taking the average of several repeated measurements. Now let's try to answer the second question. Taking repeated measurements will make my result more precise or more accurate. So the accurate result will when all the values they are close to the real value. In this case, my real value is 3 inches. This pencil real value is 3 inches. By taking the measurement on a ruler that does not have the same original calibration, will not make my value here be accurate. You're never gonna make this value be equal to this. So this is not gonna happen. Now let's look at the precise. So if I keep taking several measurements using this ruler here, all my results, they are going to be close to each other, but they are not going to be close to the real value. So that will be precise. So here it states, the measurement can be made more accurate. No, you're not gonna be accurate because it's not gonna be the same as the real value. The measurement can be made more precise by taking several repeated measurements. Yes. So the answer is D. So in summary, you have to ask yourself, is this an instrument or human error? If it's instrument, it's a systematic error. If it's human, it's random error. Question 2. Repeated measurements using expanded ruler than its original size would make results more precise or accurate. So definitely you make my results more precise, not accurate. To give a numerical example, so if you take 3 trials and you read the length of the pencil, 2.56, 2.5, 2.58, yes, they are precise because the results are close to each other. Now, when you look these here, they are not equal or close to the real value, so it's not accurate. Another question about accuracy and precision. Let's read. A man of mass 75.2 kilograms uses a set of weighing scales to measure his mass 3 times. So here we have 1, 2, 3. He obtains the following readings. Which statement best describes the precision and accuracy of the weighing scale? Now, when we look at this table, we can conclude that all these values, all these trials, they are close to each other. So we can say that it's precise. They are close to each other. However, the real value is this, 75.2. So it's not close to this. So it's not accurate. Not accurate. Real value is 75.2 kilograms. So let's read the options and eliminate some of them. Not precise, incorrect. Inaccurate, no. Not precise, incorrect. Not accurate, yes. Precise, correct. Inaccurate, no. Is precise, yes. Not accurate, correct. So your best answer is D. Okay, so let's read this problem. What is about? An analog ammeter has a pointer which moves over a scale. Following prolonged use, the pointer does not return fully to 0 when the current is turned off, and the meter has become less sensitive at higher currents than it at lower currents. Which diagram best represents the calibration graph needed to obtain an accurate current reading? And here we have 4 options. So here is a sketch of the display of an analog ammeter. So if I would connect anything, it's already showing a value right here of, let's say, 0.2 amps. 0.2, 0.3, 4, 0.5, and so on, up to 1 amp. So it's already showing this. So this is what we call zero error. Zero error. So the problem states 2 situations here. One is the ammeter has a problem with 0 error. And the second one, the ammeter is less sensitive to higher current. So as the current is getting greater, the pointer is not going to deflect as much. Now let's take a look on this graph. So all 4 graphs, they are the scale reading over the true current, all of them. Scale reading over the true current, which means the current that is flowing in a circuit. Because all these graphs, they slightly differ from each other at the beginning here, and at the end, we are going to take a look what happened in the beginning and the end of each graph. So let's start with option A. The option A is indicating from this graph that the meter is not showing any current flowing, even though there is current moving around. So there is no current here. The head of this problem does not state that the meter will not read any current. It just say as the current get higher, so you'll be less sensitive. So this is not correct. So as a note here, there is no current showing in this meter, even though current is flowing in the circuit, which means this pointer will not move at all. Now the end of this graph shows that as the current increases, now the scale is not showing that much value right here. So you see that the curve is getting like a little bit lower. So the scale does not show the same increment as the current. So exactly how the story says, is becomes less sensitive to higher current. So this section here of the graph is correct, but this is not. For this reason, we are going to eliminate option A. Option B, we have here the beginning of this graph exactly how shows on option A, which means that even though there is current in the circuit, but the end meter shows no deflection. Okay, at the end of this graph is showing that higher current, so the meter is showing also higher values, and this is not true. This is not true, and this is not true. So we are going to eliminate option B. Now let's take a look on the graph C. So in graph C shows reading on the scale, even though we have no current. Current here is 0, but it's showing already a value here, which is correct because this end meter has a problem with the 0 error. So there is a value here, even though there is no current flowing. So this end is correct. As a side note, meter shows value when current is 0. The other end of the graph is showing that higher current is not showing the same increment on the scale, on the meter, which corresponds to this statement. The meter becomes less sensitive at higher current. So this end is correct. So it looks like my option C is the one that is correct. Following the trend, option D, so here in this end, the meter is showing a value of current, even though there is no current because it's 0 error. But as the current gets higher, the increment is also higher. You see that is like an exponential increment. So this is not true. So option D is not correct. So let's read this question here from May-June 2019, paper 12, question 4. A student carried out an experiment in which an electric current was known to decrease with time. The readings he found from first to last were 3.62 milliamps, 2.81 milliamps, 1.13 milliamps, 1.76 milliamps, and 0.9 milliamps, which statement could not explain the anomalous 1.13 milliamps reading. So here is a table with the sequence of his reading. He starts with time 1, the current that is higher than time 2, and then is higher than time 3. And then we have here something that is not following the trend. The time 4 is greater than time 3. And then back to time 5, the smallest one. So something is not right on this value right here, because the correct sequence will be 2.81 and then 1.76 and then 1.13. Looks like that is out of order. So this is what anomalous is out of order. So let's check each option and read and see what could not explain this out of place or anomalous value on this table. A, he has reversed the 3rd and 4th reading in the result table. Is possible? Yeah, possible. He read the N meter incorrectly. The reading should have been 2.13. 2.13. Possible. So far 2. Let's read it. If you can find something better than that. C, he took the current reading at the wrong time. Possible. So far, all these 3 options could justify this, and looks like it's all human error. So it's the experimenter that actually did this. So let's see the last one. There was a systematic error in the reading from the N meter. So this one here, I will lift my flag, because systematic error is an error caused by the instrument. Only by the instrument. If it was a problem with the instrument, all his readings will be out of place, but just one is showing out of place. Could be that he reversed the order. Could be that he did that. Could be that he read the incorrect value from the N meter. Instead 2.13, he wrote 1.13. Could be. He took the wrong reading at the wrong time. Could be. So he was skip some, and that could be that happened. But this is not a systematic error, because there is not a problem on this N meter or whatever he was taking this measurement. So in conclusion, is systematic error. The other readings were not affected, so it's, like I said, it's systematic error. Let's read this question from the same test, but now question 6. 2 quantities P and Q are directly proportional to each other. Because of this first statement, 2 quantities P and Q are directly proportional to each other and following the same trend that I see on X and Y, Q and P, so I can draw a straight line to express graphically what this statement means. And one more thing, all values on this line are the real value, and all values on this line, they are the same, which means that the slope of this graph here will have the same number no matter which point we are going to use to calculate the slope of this graph. Let me keep reading. Experimental results are taken and plotted in a graph of Q against P, which graph shows there were random error in the measurements of P and Q. Random error. So let me start by saying that systematic error are affected by the instrument. So if I'm using the same instrument with the same problem, I'm going to have all values about the same range. Random errors are caused by the experimenter. Could be his reading strategy is not correct. Could be that he is not reading using eye levels. The eye level type of reading, he's causing parallax errors. So random, usually they are values, they are, like the name suggests, they are kind out of place. They are kind close, kind of, but a little bit off place, not like systematic. Systematic, usually they are together, and random, they are a little bit displaced. So let's eliminate some graphs. Let's look at graph B. Graph B is not a line. It's kind of a little bit slightly curvy here. So this, it gives a sense of that is not proportional. So the increment of P and the increment of Q, they are not proportional to each other. Because you see here we have, let's say, some point you are not going to have the same increment on the Y as you have on the X. So for that reason, B is being eliminated. Graph D. Graph D is showing a value here, even though there is no value for P. So Q already starts with a value right here. That is an indication of systematic error. Specifically zero error. So which means that the instrument is already set up with a value right there even before using. So that is systematic. And here is asking which graph shows there were random errors. So that is not going to be on D because D is showing systematic error. So I'm going to eliminate this one. Now I have graphs A and C. Both are directly proportional, which is great. But this one here, let's start with A. Most of the values, they are on this graph. This is not a sign of random error. Random error should be some points above and below this graph, because this random error, right, is caused by human mistake, human error. So here is just one out, but C is showing a more inconsistency with those values. That's why this line probably is the line of best fit. So you have the values above and below around this line. So this is a sign of random error, which is more inconsistent. Inconsistent. Caused by the experimenter mistakes. So the answer is C.